And I think we are live. Welcome, everybody. I am Mat Kaplan, the host of Planetary Radio for the Planetary Society, and it is a delight to welcome you to this special planetary defense update from the Planetary Society. And I want to thank you for joining us. Even bigger thanks go to all of you who are members of the Society or who directly support our planetary defense and other efforts. Many of you have done both, and most of you know defending our homeworld is one of the Society's core enterprises. We may leave you wanting to learn more about our work after watching this, or maybe you'll want to join the fight to, as Bill Nye puts it, save the world. Visit us at planetary.org/defense, and that's where we have lots and lots of resources and a very easy way to become part of our planetary defense team if you're not already on that team. The great people that I'm about to introduce you to are all leaders of this grand endeavor. You know Bruce Fetz and Casey Dreier and I are colleagues within the Society. We'll be introducing Bruce and Casey in just a moment, but first I want to introduce you to one of our best friends and partners. Astronomer Amy Mainzer is a professor and researcher in the University of Arizona's Lunar and Planetary Laboratory. She worked for many years at the Jet Propulsion Lab near Pasadena, California, and remains the principal investigator for NASA's NEOWISE mission. That's the Near Earth Object Wide Field Infrared Survey Explorer. And I bet a lot of you were outside a month or two ago watching that gorgeous comet discovered by her spacecraft and named for it. She's also deeply involved in a future mission that all of us at the Planetary Society have been advocating for. She'll tell us in a few minutes about the NEO-Surveyor Space Telescope, and I suspect that our other panelists will have something to say about that mission as well. Boys and girls know her from her appearances on the PBS Kids series Ready, Jet, Go. And Amy is a recipient of NASA's Exceptional Scientific Achievement Medal. Amy Mainzer, thank you very much for being part of our presentation today.
Yeah, thanks so much, Matt. It's really great to be here, and I really appreciate everybody tuning in to learn a little bit about our nearest neighbors in the cosmos. It's really great to have everybody here.
You're going to be the first person we go to for your own update, a little presentation, but first, let me read similar introductions for our other two participants. Bruce Fetz is the Planetary Society's chief scientist. If we had a chief engineer, he'd probably be that too, and the program manager for our Light Sail program. But wait, there's more. He administers many other efforts, including our successful Shoemaker Near Earth Object Grant Program, which I'm willing to bet he will talk to us about today. He often helps to plan and represents the Society in gatherings like the biannual Planetary Defense Conference. Bruce is another NASA alum. He spent several years with the Planetary Science Institute before we got him. Like Amy, he has had his share of media appearances, and Bruce is also the author of a series of books for young people, the latest of which is Space Exploration for Kids, a junior scientist's guide to astronauts, rockets, and life in zero gravity. He has also been my partner across nearly 18 years in the What's Up segment of Planetary Radio. So Bruce, welcome to you as well. Thumbs up, that's good enough. Last but far from least, Casey Dreyer is the Society's chief advocate and senior space policy advisor. That makes him a public face of our efforts to advance our mission in DC, working with Brendan Curry, our chief of Washington operations. As his bio says, Casey is passionately committed to demystifying the politics and policy process behind space exploration for all audiences. He is a trusted source for journalists and has been featured in many publications. He's also the author or co-author of many of our position papers, including a recent white paper regarding planetary defense that was submitted to the National Academies of Science, Engineering, and Medicine as part of the latest Planetary Science Decadal Survey, the one that is currently underway. He has also produced unique and very revealing analyses of NASA spending that have become important tools for many policy officials, academics, and reporters. And I believe he'll be sharing a little bit of that with us today as well. Casey also joins me each month for the Space Policy edition of Planetary Radio. The next edition of SPE is coming right up on Friday, September 11th. Casey, welcome as well to you.
Thanks, Matt. Happy to join all these people with much higher degrees than I to chime in a little bit on planetary defense.
And me as well, I'm sorry to say. Many of you out there, I know, are looking forward to being able to ask your questions and join us here as a part of this broadcast. We look forward to taking as many of those as possible. As usual, it's unlikely that we will get to all of them. It'll be my job to sort of consolidate those and filter them. Keep in mind, if we don't get to your question, you will be able to submit them offline later on as well, and we will do our best to get to those too. We're going to hear from each one of our panelists in turn before we start to go into a general discussion. And the first person we're going to hear from is Amy. And Amy, for us to do that, I better make you the presenter once again, and we'll see if you're able to share your slides. Give that a shot now. You should be able to if it works.
Okay, so let's see here. We will try to see if we can get some success here.
While you're doing that, I'll mention, here's something that already came in from Mel Powell, who I know is a regular listener to Planetary Radio. He says, hello, Matt and awesome team. For today's event, we're not allowed to root for the asteroid, right? Just checking, been a rough year. Yeah, Mel,
it's not going to hit us on the right before the election, I think, to the chagrin of many people. It'll miss.
Mel, I kind of like this planet. And, you know, Elon Musk's efforts to the contrary, we're not ready to go anywhere else yet. Amy, I see your first slide, so take it away.
Fabulous. Okay, well, yeah, so I think this is just a great opportunity to just give everybody a little bit of an overview about planetary defense in general and just some of the specific areas that we've learned a lot from and just where we'd like to go in the future a little. So one of the more recent events that has happened was in 2013. There was a huge fireball that exploded over Russia. And here are a couple of stills. The reason that we care so much about this event is that it's really one of the best studied in recent memory because of all the wonderful footage that people were able to gather from dash cams, from security cameras, and just, you know, your people's iPhones, that they were able to snap shots of it. This was a pretty large explosion, and it occurred completely by random coincidence on the very same day that another asteroid was predicted to make a very close approach, but not hit the Earth. So from my own recollection of it, I remember I was driving in the car, and I think I was driving home from the airport and listening to the BBC radio, and they said that there's been an asteroid impact, and I thought, but that can't be. We knew with great certainty that this object was not supposed to hit. As it turned out, it was a completely different asteroid, and this was just an enormous cosmic coincidence that the one that you see here exploded in spectacular fashion over Russia. The object was small enough that it didn't cause any real appreciable damage. It did break a lot of windows, and I think it injured about 1,600 people, but it didn't cause any more damage than that, which is a really good thing. So you can get an idea of just what some of these things look like. It's a huge explosion in the upper atmosphere, and part of the way that it was figured out what was going on right away is that the explosion really happened at very, very high altitude. So that's kind of a recent event. But you know, let's take a step back for a minute, and when we talk about near-Earth objects, let's just have a little bit of background about what we really mean by that. In this case, there's sort of two classes of objects that you can think of. There's asteroids and there are comets, and they're kind of you might almost think of them as sort of opposite ends of a spectrum, really. On one hand, you have asteroids, which are rocky bodies that are, you know, everything from very kind of weakly held together clumps of gravel almost to really nearly solid slabs of nickel and iron. So they have a lot of diversity in their types and their densities, shapes and sizes. And they can be pieces of other asteroids that have sort of re-agglomerated back together. And you can see an image here of an object called Itokawa. That was an asteroid that was visited by Japan's Hayabusa mission, and actually a tiny little sample was retrieved from that. On the other end of the spectrum, we have comets, which are very black and carbonaceous, carbon-rich objects that have a lot of different ices mixed into their rocky matrices. So they've got a lot of stuff in there, a lot of different volatiles all mixed together and kind of frozen in place. And they mostly spend a lot of time in the outer solar system. So those ices tend to stay more intact. Whereas the asteroids, because they tend to make closer approaches to the sun, some of them tend to be less volatile rich, although not always. So that's kind of what we see when we look at these objects, when we can actually visit them with spacecraft. But sometimes they visit us, and it can cause some considerable damage. The Chelyabinsk object was small enough that it didn't really make much of an impact through the Earth's atmosphere, just the shock wave. It exploded up in the upper atmosphere, and the shock wave propagated to the ground. But that object was only about roughly 20 meters across, so kind of house-sized, if you want to think of it that way. But if the object's a little bit larger than that, or made of a more dense type of material, it can actually cause an appreciable crater on the ground. And here are a few examples. The Tunguska explosion in 1908 knocked down a lot of trees over hundreds of square kilometers, but it didn't leave an actual crater. However, other ones are seen here to the right. There's one here from India that was thought to have impacted about 50,000 years ago, and that's about a kilometer across. But there's a much larger one up in Canada produced by a pretty large impactor. And of course, there's the really big one that you might be familiar with in Chicxulub, which is in the Yucatan Peninsula. This was a really big object. This was somewhere in the neighborhood of 5 to 10 kilometers across, and it just packed an enormous amount of energy when it impacted the Earth. Basically, these objects move with incredible speed relative to the Earth, and that's why they can really pack such a punch. In this case, you can even see a ring-shaped crater that is visible in this radar image here, taken by NASA. And of course, another event that was a little less recent now was a comet discovered in 1992 that was observed to impact Jupiter. And I think there was some debate at the time as to whether or not the comet would really leave any appreciable marks on Jupiter, or would Jupiter just sort of swallow it up. And what we saw, what scientists saw with Hubble Space Telescope was, of course, the impact left big marks. And each one of these marks here is sort of roughly the diameter of the Earth. So that certainly got people's attention. And as a result of all of this, more systematic surveys for near-Earth objects have now been taking place with better and better telescopes and better cameras. So it all sort of begs the question, how often does this happen? The good news is it's extremely rare. It's really, really, really rare. And we know that it's very rare because, we're still here, right, as a species. And we know that really, really large events like the one that wiped out the dinosaurs, the Chicxulub impactor, those sort of only happen once every 100 million years or so. So that's great. But smaller objects happen much more frequently on a geological timescale. And when we get down to objects as small as the Chelyabinsk impactor, it might be one every few hundred years or several in 100 years. But the thing is, these things don't happen really on a super regular cadence. They are individual events that occur, and well, kind of the race is on to figure out when the next one will be and how severe it will be. So from my perspective, this sort of boils down to a few critical questions that we would like to understand. We'd really like to know when the next major impact would occur, and we would like to know what its severity would likely be. To answer those two questions, of course, we need to find the objects and get good orbits for them, orbits that are good enough that we can reliably predict where the object is going to go. And of course, the how bad part really boils down to measuring the kinetic energy of the impact. And that in turn, this is my one equation here, basically scales as the mass times the velocity squared. Well, we get the velocity of the object relative to the Earth once we know its orbit, but the mass depends very strongly on the diameter. And you can see here that it scales roughly as the diameter cubed. So it's pretty important to know the diameter. And of course, we also want to know the density, the size, the shape, how it spins, whether it's a solid body or a gravel pile, lots of things like that. But to first order, we need to know when and how big. So NASA has been tasked by Congress with doing this work. And initially, Congress gave NASA the goal of finding 90% of all the 1 kilometer and larger near-Earth objects and to track them. That was in 1998, and it took the community roughly about 10 years or so to complete this objective. So the good news is now we know of where more than 95% of all these 1 kilometer and larger near-Earth asteroids are, and we've really got good orbits for them, and none of them pose any sort of impact hazard that we know of. So that's great. Those are the objects that are capable of causing, global damage, very severe. And now the objective has moved down after it's been after that big one was sort of crossed off. Now we've moved down in size to the objects that are large enough to cause what we would call severe regional damage. And that's about 90% of the objects larger than around 140 meters in diameter. So we'd like to be able to do that. Congress said we should do that by 2020. It's 2020. As of right now, about 2/3 of those objects remain undiscovered. So we're making some progress, but there's still quite a long way to go. And when we get to objects the size of the tiny Chelyabinsk impactor, it's just 1% or so. This is just a short summary of some of NASA's assets that are being used to do this kind of survey work, and their telescopes in Hawaii, in Arizona, and even in space. So we have a variety of telescopes operating now. This one in particular is the project I've been working on. This is the Wide Field Infrared Survey Explorer, and this is a telescope that really wasn't designed to do this kind of work. Originally, the original principal investigator, Ned Wright, designed it so that it would make a very big map of the sky in infrared wavelengths. It turned out pretty good for looking for asteroids, though. And with it, we have still been able to keep it running, even though it was really only supposed to last for 7 months. Here we are, 10 years later, with 2 of the 4 channels still operating and looking for asteroids and comets. So anyway, we've found quite a few. We've detected quite a lot, and we've been able to detect a sample of near-Earth objects, but we can't quite make that 90% limit. That's a toughie. So anyhow, just to kind of wrap up here, it is a team sport, planetary defense, and the data that is taken in every year comes from many, many dozens of countries and observers all around the world, including the big surveys that I just talked about, as well as lots of people who are doing this work as I would call them unpaid professionals. So we really appreciate all of their contributions, and the Planetary Society has been really a big part of that. So with that, I'll turn it back over to you guys.
Thank you, Amy. That was a great introduction. And yes, indeed, those so-called amateurs are something that I'm sure Bruce is going to tell us. Bruce, before we get to your presentation, I'm just wondering if everybody brought their asteroids or their meteorites. I mean, there's mine. And no, it didn't land on Earth with that pin, but does show you that it's one of those nickel iron, really dense little rocks that was given to me by a friend who found it in the Sahara Desert some time ago. Amy, you brought a sample or two, didn't you?
Yeah, so I actually have here a piece of the rock itself. This is a piece of the Chelyabinsk meteor that exploded over Russia. So you can see what it looks like. It's got a burned outer crust. This is called a fusion crust, and it didn't have this when it was floating in space, but when it passed through the Earth's atmosphere, this teeny little piece actually made it to the ground. You can see on the inside, it's a pretty stony object with lots of little kind of inclusions in there. And you can even see, I don't know if you can see this on the camera, little cracks and little kind of lines running through it that indicate that it had probably collided with other asteroids in the distant past.
Great. Hey guys, did you bring yours? Got an asteroid for us, Casey? Casey, I think you're muted.
Not exactly an asteroid, but I do have a little bit of Martian meteorite, tiny, tiny little bit that my budget would allow me to acquire. But those aren't the frightening ones that I'm aware of. Maybe Amy can correct me on that.
Well, that's a really rare specimen right there. That's really neat.
You haven't eaten any of it, as Kim Stanley Robinson, the science fiction writer, did, have you, Casey?
I haven't joined that particular religion yet, no.
Bruce, show us yours.
Well, I've got this, and it did come to Earth with the Planetary Society logo on it, and it's made of an unusual material for an asteroid.
I'm not familiar with that taxonomic type, Bruce.
This is it's an R type. It's a rubber asteroid.
Very important to roll the R when you describe that class of.
Matt's the expert. You sound kind of quiet, Matt. At least to me.
How about now?
Oh, you sound glorious now.
Oh, that's better. Okay, I apologize. There was a button that I pushed and didn't push a second time here on my end, a physical button. Bruce, now that you can hear me, I can tell you that we're ready for you to go into your presentation. Tell us
All
about
right.
what the Planetary Society's role is in all of this.
Can you see my screen?
Not yet.
Ah, oh. Keep hitting buttons. It does not want to play.
Uh-oh. I'll tell you what we might do is we can go to Casey. I can make him the presenter while you play with that a little bit. These all work just great, of course, during the rehearsal.
Well, wait a
Always, that's
second.
showbiz.
Are you sure you're shared
Again?
with?
Let me make sure it's on you. Yeah, it says it's on you. Let me check it a different way.
I have a grayed out screen.
I do show you as the presenter here. Let me take it away from you and give it back. It helps at all. We'll just spend another couple of moments doing this.
Meanwhile.
All right, I went back to Amy and Bruce. I'm now going to try and get it back to you.
All right.
Okay, says you got it again.
Ready. Show my screen. Anything?
No, I'm afraid not.
Well, that's odd.
Sorry about that.
Mine worked perfectly before. Well, let me go to Casey. I will fiddle, and then I can always just mime my presentation if needed.
Casey, I hope we do. I hope we do a little bit better with you. Give it a shot. I'm making
sorry,
you.
Man.
Casey, I just made you the presenter. Take us through a little bit, and yours is working. We see your slide. Tell us what we're looking at.
Well, I just want to give a basic budget context for what we're talking about here with planetary defense. So planetary defense, one of the most important things to think about in terms of how NASA approaches this, and particularly from the United States here, is that this is a very new field. As Dr. Mainzer kind of implied through her a couple of slides there, it's really only in the last 30 or so years that the extent of the threat has been understood and efforts to understand the distribution, size, and orbital locations and characteristics of near-Earth objects has really been attempted. NASA has led the charge here in the United States, but their budget has really just been minimal. It was not until the last decade that near-Earth observations efforts at NASA grew above single-digit millions of dollars, right? So we're talking about $3 to $4 million a year for the first 15 years of NEO observations. This is out of a budget of billions of dollars, right? We have seen, relatively speaking, incredible growth in planetary defense spending in the last 10 years. But again, this is relative to a very small amount. So an incredible growth of a small amount is really a modest amount here where we are at the end. And just as of last year, we're at about $150, $160 million spent by NASA on planetary defense activities. The vast majority of this growth has been associated with really the first flight mission of planetary defense, which is DART, the Double Asteroid Redirect Test, which will be practicing, will slam itself into a small asteroidal moon here in the next few years. The size of the budget that we're talking about going forward with is really not enough to accommodate the mission we'll talk about here in a little bit, the NEO surveillance mission that Dr. Mainzer has been working on for many years now to try to launch a space-based telescope specifically to search for near-Earth objects. So while the budget has gone up, it's been good. The overall amount is still pretty minor. And just again, to put this in context, the overall argument for planetary defense has not changed in 30 years, right? It's pretty clear what the consequences of not knowing what things out there are, right? We need to understand the level of threat. So why did the budget grow? And this was an attempt to kind of associate, a lot of the growth has been associated with shifts in NASA priorities, specifically during the period where NASA was briefly going to send humans to an asteroid. That's where the broad policy goals of NASA's human spaceflight program aligned with the goals of planetary defense through NEO observations. And that's where you actually saw a doubling and then quadrupling of its budget over the course of just a few years, because for a while, human spaceflight wanted to find where near-Earth objects were in order to send humans to them. And that continued to grow again. All that growth has been seen with the mission flight line. And now the future here is very uncertain. Ideally, we want to grow this program line up to about $200 million a year. That's less than 1% of NASA's overall budget. If we could keep it at that point, we could have enough money to pursue a mission like NEO-SM in the next decade and continue searching with these ground-based telescopes that Dr. Meinzer talked about. So I'm happy to share this with anybody. This is all public on our website. But fundamentally, again, growth in planetary defense, this has been very new. And we're still in the early stages of establishing kind of the bureaucratic home within NASA to really be able to fight for its own resources and attention, even though it's an incredibly important program itself.
Casey, as you and Brendan Curry walk the halls of Congress, what's the general attitude that you find nowadays toward planetary defense? Is it bipartisan support, or do you find less than that?
Well, generally not getting hit with a giant asteroid gets very good bipartisan support. It's not in the platforms of either Democratic or Republican circles to be hit by an asteroid. But it's more of an issue of priority. And it's one of those issues where, because it's a new program, right, relatively new concept, right? Again, the last 30 years, NASA was not designed initially to search for near-Earth objects, right? The US Constitution did not establish searching for near-Earth objects as a priority of government. And so as this has become better understood, establishing kind of the bureaucratic superstructure for it to exist and then grow its own resources, that takes a while to develop. And so the fact, in a sense, that these missions are so modestly priced, ironically makes it harder to gain political support, because it doesn't, in a sense, drive enough resources back to various congressional districts. It doesn't raise to the awareness of a lot of levels of politicking and spending, because it's so affordable. And so while, of course, people tend to really embrace the idea, keeping that focused attention on it and understanding the priorities and the value of the investment is really important. And that's actually something we've been working on in terms of messaging, a paper we submitted to the upcoming decadal survey process, which sets the priorities for NASA's Planetary Science Division in the next 10 years. We argued that we can use the current framework of understanding COVID-19 pandemic. It's a natural disaster. It's an unlikely disaster situation that we find ourselves in. High impact, low probability. Asteroid impacts are kind of the ultimate high impact event, right? Low probability, but associating that and having the experiential framework that everyone has now with the consequences of not properly preparing for these types of things, I think we can better talk about the importance of planetary defense for how we can do things now that'll minimize consequences in the future. And a big part of that is just inoculating ourselves against future outbreaks, in this sense, searching for the threatening, potentially hazardous asteroids that may or may not be out there.
Casey, that white paper that you and I think you collaborated with Bill Nye, our CEO, on that was submitted as part of the decadal survey. It is a terrific read. It is available on our website, right?
That's true, yep. On our articles section and in our new space policy section of our website lists the paper.
All right, thanks, Casey. Bruce, you want to give it another try? We'll give your slides a shot, and if they don't work, we still want to hear from you.
Thanks.
Oh, I better make you the presenter here.
That would help.
I'm doing right now. It's always a good step. Okay, give it another shot.
All right. Anything?
No, I'm afraid not. Don't know what happened there. I think you've been edited by the GoToWebinar, or censored by the GoToWebinar platform. I apologize for that.
Just because the pictures they had of you in it, you censored it. Yeah, I just got grayed out.
No comment.
Well, that's okay.
Yeah, I don't see it. Give us your end of what the Planetary Society is doing as part of the planetary defense effort that complements what Casey's up to.
All right, so the first picture is a painting of the Earth with an asteroid about to slam into it. And then we go on to the second slide. And we have a picture of meteor crater with a circle with a cross through it. Why? Because we don't want large, dangerous impacts to happen again. So one of the things we've done as Planetary Society is establish a
Oh my God, your slides just showed up, Bruce.
Wow, there they are.
Unusual.
Just give thanks and move on.
Thanks, Matt. All right, so 5 steps to prevent asteroid impact. This is in some ways a repackaging of what the planetary defense community agrees upon, but we tried to put it in a way that's easily communicated. So you need to find the asteroids. That's what Amy's talking about, and is obviously if you don't know it's there, you can't know whether it's going to hit Earth. You got to track the asteroids. Lots of follow-up observations to give you the orbit, because it doesn't do you any good to know the asteroid's there if you don't know if it's going to hit Earth. Characterize the asteroids. This is everything from what NEOWISE does in their studies to what amateur astronomers do and professionals from Earth, figuring out things like spin rates and what the range of objects are and which ones are binary, because you really don't want to be ready to deflect a single asteroid and then find out, oops, it's 2. Deflect. So if there is a dangerous asteroid, you want to figure out obviously how to deflect it. In other words, change its orbit just enough so it clearly is going to miss Earth. And then this last piece is also important, which is internationally coordinate and educate. And that's a lot of, particularly the education, what we've tried to focus upon, but also that all the countries are involved, because you never know where these are going to hit. If one hits, it's a global disaster. And as you change that orbit to make it miss Earth, well, you're moving the target point across the Earth. So everyone needs to talk ahead of time. And so we're involved, for example, we were involved with the United Nations and putting together recommendations that have since been followed to have coordination groups between different countries. Since 1997, we've run the Gene Shoemaker Near Earth Object Grant Program, named after planetary geologist Gene Shoemaker, who was a pioneer in impact and cratering. And we give grants every couple of years to mostly amateur, or as Amy correctly said, unpaid professionals, considering the quality of their work. Unpaid professionals, we give grants to upgrade their telescopic facilities with new cameras, with reluminizing mirrors, etc. This is one of the prettiest award winners. This is in Croatia, and they just won an award this last year. And mostly what they do is asteroid follow-ups and characterization, so that figuring out lots of observations to find orbits of things that have been discovered by the professional surveys, or doing characterization, figuring out if they're binaries, figuring out spin rates. Occasionally, they still discover things. We'll talk about that in a moment. 2019, we awarded about $58,000. This, by the way, as with all our programs, obviously is completely due to the members of the Planetary Society, members and donors that enable us to do this type of work. We gave to 6 applicants from 4 countries. There are pictures of them, and they're tiny telescopes, which in some cases are very much not tiny. Over 22 years history of the program, we've given about $500,000 to 62 awards in 19 countries. Here's a map showing the distribution of the awards we've given. So you can learn more about this program on our website. I'm going to keep saying this, but go to planetary.org/defense, and that will get you a place where you can find links to things, including this, which a few months ago, a few of us visited the California desert, the Center for Solar System Studies, where they've got a bunch of telescopes that they can operate remotely from around the country. And the 3 of our winners actually house telescopes out there. So we've got a fun video and a nice blog about that. Here's an interesting story. One of our winners, Leonardo Amaral, who won this last year in Brazil, actually has discovered a comet. So there's now a Comet Emerald, which does not come anywhere near Earth. But, and we haven't even put this out there, he just discovered one of that probably. It's around 1 kilometer diameter. So the things Amy mentioned, we found 95% of, he's found one, and that's largely because he's located in the southern hemisphere. And that gave big brownie points when we were looking to do awards, and it's paid off. He found this very large NEO just in the last couple weeks. Oh, by the way, it's not going to come anywhere near hitting.
Phew.
Little details. We've also got cool products from a Kickstarter we did, Kick Asteroid Kickstarter, including posters like this one. Hey, asteroids, next time we're coming for you. And then stickers, some of the famous craters, the Stay Unextinct encouragement pin. You can find those things at planetary.org/store, as well as other Planetary Society goodies. We've got downloadable infographics, so we encourage you to go share information in your community about planetary defense. We've got infographics and a toolkit. This is just one of them. You can find those again, planetary.org/defense. We've got a series of random space fact videos that pose the profound question, what would happen if the dinosaurs had had a space program? So anyway, my dinosaur friends and I made some hopefully humorous and educational videos, and then I took those and turned it into a 1-hour class with additional lecture on the teachable interface, which you can find Asteroid Threat 101, also at planetary.org/defense. Every couple years for the last almost 20 years, there's been a planetary defense conference, and we've been a primary sponsor of it for a long time. And what's great about this conference is it's the one time where you really get experts in all aspects of the problem, all 5 parts of the plan I mentioned, as well as disaster response, what if it did hit, the policy side that Casey's talking about. So you get everyone in one place. It's supposed to be in Vienna in April of 2021. It might, of course, end up being a hybrid or virtual conference. I've served on the organizing committee for a few years, and every time, at least the last several, we hold a TPS public event. And we will do that again this time, either in Vienna or virtually, like this one, bringing together experts like Amy and talking probably with that crazy guy on the left in the lower left picture. What is Mat Kaplan? All right, that's my summary. Basically, again, we can't do this. We can't support planetary defense as one of our core enterprises or do any of our efforts without members and donors and people getting involved in space exploration and saving the world. So go to planetary.org/defense, planetary.org/store, and always keep your PowerPoint working when you do a webinar. Thank you.
Have to unmute. Bravo, everybody. Thank you so much for those presentations. The questions from those of you who have joined us today are pouring in. Before we start to get to those, and we will right after this, we're going to try and share a special little treat with you. And to do that, let's see if I can get to all the stuff that I need to be able to do that here by making me the presenter again. Yep. What I'm going to show you now is a random space fact video that Bruce happened to be part of during a planetary defense conference where people from around the world gathered in Italy, outside of Rome, in a beautiful little town called Frascati. And I think you'll see a surprise guest appear in this. Let's see if we can roll that now.
NEOWISE is a space telescope that's focused on finding and characterizing near-Earth asteroids. It looks in the infrared part of the spectrum. That allows it to see the heat from the asteroids, making it very good at finding darker asteroids, ones that are dark in the visible. This has allowed it to find almost 5 asteroids!
Hello, Bruce.
Hi, Amy. This is Amy Mainzer, Principal Investigator for NEOWISE. How'd I do?
We found a few more than almost 5.
So like 5?
Keep going.
10?
A little more.
100?
try over 34,000.
Over 34,000?
Yep.
And you didn't see the one coming down that hit me?
Actually, we did. All right, ready?
Yeah. Want to learn more about planets and astronomy? Check out my free online course at California State University, Dominguez Hills, Introduction to Planetary Science and Astronomy. Go to planetary.org/BetsClass.
Nice work, folks. Okay, we are ready to start getting to your questions. And again, I'm going to be consolidating these because we are getting a lot of similar ones. Let's start with an aspect of planetary defense that we haven't really talked about yet. We've talked about finding them, characterizing them, how we do that. And there's a lot more to say about those as well. But what happens when we find the one that has our name on it? Among others, we got this question from Robert McMurray, I hope I have that right, who's wondering what's the current thinking about what we're going to do to deflect these. And Amy, maybe you'd like to start with this. I know we've got a big attempt that's upcoming fairly soon where we're actually going to try and nudge one of these rocks.
Yeah, that's right. And it's a really important question. Of course, we have to be able to do something about it, hopefully, and not just find them. So what we can do depends a lot on the circumstances. Of course, it depends a lot on how big the object is, how much time we have before the impact, and just the nature of the impactor itself. So this is why when we try to go look for these things, we want to try to find them when they're many years away from an impact so that we have time to consider all the available options. The DART mission is going to test a particular strategy, which is to just simply bump into it and try to nudge the object out of the way with a kinetic impact. So that's just a fancy way of saying bump into it and push it. So basically, they're going to get out there and try to shove the asteroid into a slightly different orbit to just see if it can be done. If you have enough time and the object's mass is well understood and its internal properties are understood and all of this, that might be enough. There are other techniques that people have talked about, and there are things that range from everything from using lasers to push them, or even painting one side of the asteroid a light color so that the very gentle pressure of light will just gradually drift it away, to parking something massive next to it, a big massive chunk of metal spacecraft, and using the faint force of its gravity to tug the asteroid out of the way. There are lots of different options. And of course, there is also the option of exploding an explosive device near it and trying to push it that way. Ideally, though, we'd like to use the least amount of force that you can use safely because it's just less complicated for lots of reasons. So that's why DART is testing the kinetic impactor first. Just pushing the object is probably in some ways the simplest approach and the most easily understood.
I love that idea of little robotic taggers going out there and painting one side of an asteroid.
Yeah.
Get off my asteroid. Bruce, do you want to add anything to that? I mean, this is something that you've played a big part in. And one of the things that happens at the Planetary Defense Conference, and you're a major participant in this, one of the planners, are those tabletop exercises about what we're going to do to respond as a planet.
There are. So most every planetary defense conference, there are simulations that go throughout the week where people come up with, hey, there's an asteroid that was detected. It's kind of got this orbit. What do we do? And then things just progress with time over the course of the conference, and you see what you learn from the whole process. But no, Amy did a very nice job overviewing the major deflection techniques. I don't think the tagger option is really high on the list, but everything's in the mix right at the moment.
Casey, how much discussion is there of this part of planetary defense in Washington and maybe other world capitals?
I mean, certainly part of the discussion. It's telling, I suppose, that the first mission of the new flight program for planetary defense is a deflection test, right? However, I just want to emphasize what Dr. Meinzer said about how important the early detection is, because that really increases the number of options that you have to respond with. the closer you find it to when it impacts Earth, the fewer options we're going to have, because it takes time to build spacecraft. It takes time to launch them. We're at the mercy of orbital mechanics when it comes to engaging with these things. And so that's where you really have to know where they are as early as possible to give yourself the maximum number of options to deal with. Something else just to keep in mind is that when you're engaging with these things, the amount of mass you can throw at an asteroid is dependent on the types of rockets that you have. So this is one of the good arguments for having heavy lift vehicles, launch vehicles at the ready, even as a national asset, even if you don't use them much, to be able to throw a lot of stuff at a potential asteroid, because you can't just invent a rocket, test it, build a spacecraft, put it on there, launch it, in time necessarily, if you only have a few years to deal with this. So there's a lot of additional things beyond the concept of the technology themselves. It's how you get to it and how much time you have that really is going to be important aspects of this.
Let's go on to another question. This one from Craig Backus. Thanks for joining us, Craig. He's asking, how do we know the percentage of undiscovered objects? Isn't part of being unknown mysterious? I would have said unknown. Amy, you want to take that?
Yeah, and that is also a really important question, because of course we spend a lot of time trying to figure this exact question out. How do we know when we're done? How do we know that we've found 95% of the really big objects? How do we know that we found 2/3 or 1/3? The way we do this is there's a couple of different techniques. You can think of it as, the first technique is basically just saying, well, we know what we've discovered. Each asteroid, as it gets discovered, asteroid or comet, gets a unique identifier. So we know its orbit, and as Casey said, we try to know the orbits as well as we can, as long in advance, so that we can basically reliably match up potential new discoveries and see if it's something we've already seen before. So one technique is to basically see how often we are finding new objects compared to how often we're re-observing the same ones we already know about. So we just look and we see, if you get to a point where you're really not finding a lot of new things and you just keep re-observing the same objects that we already know about over and over and over, that's one indication that you're running out of new stuff. Another technique is a more statistical approach, where you don't make any assumptions about the known versus unknown, and instead you focus on building a model of the asteroid population and building a model of your survey. You validate that model by looking at the known versus unknown, but then you basically tune your model until what you see with your synthetic survey matches what you actually saw. And at that point you can say, well, this means there are really this many asteroids out there and we've only found this fraction of them. So there's two complementary ways to kind of get at this problem, and astronomers use both. And it's definitely a case where we really do want to know with pretty good certainty that we have actually reached those 90% completeness limits. And like Bruce said, occasionally, even at 95% completeness for the very largest of objects, occasionally we still find the odd pretty large one out there. That said, even something 140 meters is still plenty large.
Yeah, that'll ruin your day.
Yes.
We're getting some questions from several people. Here's one from Jonathan Morgan that are along the same lines. Jonathan says, thanks y'all for doing this. Forgive my ignorance. Of course, Jonathan, that's why we're doing this. How do you all even find these objects in space? They seem so small compared to all of space. He can't even find his keys in his house. Nicely done, Jonathan. I think this is a nice opening for us to talk about some of the things that are being talked about right now and have come up already. Amy, you talked about NEO-SM, the follow-on to NEOWISE, a space telescope that you've been looking forward to for a long time, and so have the rest of us.
Yeah, so I mean, this is how when we first spot an object, the process of discovery is multi-part. We don't know what we're looking at when we first see it. We just usually see a collection of snapshots that shows a dot moving across the sky. But we don't know whether it's an asteroid we've already seen before, or is it something totally new, or worse, could it be a collection of noise or artifacts that's not even a real asteroid at all? Or maybe even worse, stars. Hate those. So what we try to do is we basically collect these detections of a potential moving object candidate. We link them together, compare it with what we've already seen. If it looks new, then we go out and we try to get more observations of it. So one of the things we'd like to be able to do is we'd like to be able to spot these things when they're further away, which is what allows us to predict the orbits further in advance. So to that end, we've been looking at ways to try to build more sensitive telescopes that can cover large areas of sky, and in particular, the region around the Earth's orbit, which is where the most hazardous asteroids tend to spend a lot of their time. So from that perspective, we've been looking at trying to build a new space telescope that is more sensitive than what we have today, both on the ground and in space. And the idea would be to just have a telescope that's really dedicated to this task, that just sits out there and looks to make these little connections of dots that we can link together and discover a lot of asteroids that way, as when they're quite a distance away from the Earth.
And if anybody else has anything to throw in, Bruce or Casey, you are certainly welcome to jump in and do that. NEOSM, as important as it will be, there are those surveys done from Earth, which some of which surfaced already in some of the images that we've seen. I'm also wondering about radar. For example, Arecibo, that beautiful big dish, which right now is out of commission because of that cable that broke and damaged the dish and some of the electronics up there suspended at the focus of the dish. Is that a major loss, at least a temporary loss, for our research on near-Earth objects?
So radar is an incredibly important resource for looking at these objects. I mean, when we spot them with our telescopes, we're looking at these things at humongous distances, and they are just tiny little dots of light. We don't usually see any real detail about them. Occasionally, we can see the light going up and down, getting brighter and dimmer as non-round objects rotate. But sometimes we really want to be able to get a closer look at a particular object. And when we get the opportunity, if something is big enough or it gets close enough, we can sometimes zap it with a radar beam from a couple of our radar telescopes here on Earth, one of which is Arecibo, which is a really enormous radio dish that's actually built into a natural valley, and it's supported that way. So what that radar observation can give us is a whole bunch of information. Basically, it can give us a very detailed look at the object's orbit. It can tell us something about shape, size, how it spins, whether or not it's got boulders on the surface in some cases, if we can get a really detailed look at it. So it's a really important way to get very detailed follow-up information on targets that are really of particular interest. But yeah, the cable is a bummer, and that will get fixed in due time, I think.
Yeah.
Right?
Matt, just a bit of connection for me. I actually spent the swan song of my brief scientific career at Arecibo studying near-Earth objects through radar and trying to make a shape model, a 3D shape model with very bad data. That was my one connection to this field, but it is an amazing resource. And Amy, I was wondering if you could talk a little bit about why ground-based observations of near-Earth objects, what pitfalls those have, or why aren't those perfect? Why do we need something in space beyond just using the telescopes that we have?
Yeah, so I mean, it really is a team sport. And I think, Bruce, you highlighted that when you talked about some of the many observatories all around the world, especially in the southern hemisphere. The way I look at this is you have a lot of different zones of space that we want to be able to cover and look for these objects. Some telescopes are better at looking at certain patches of sky, others look at different patches of sky. So there are complementary techniques. There's also complementarity in wavelengths as well. The ground-based telescopes are using optical light, visible light, like what our eyes see, to search for the objects. And that works very well, although it is harder to spot some of the objects that are extremely dark. And I actually have a meteorite here, a different one. This one is not Chelyabinsk, but this is a so-called Carbonaceous Chondrite. And if I hold it up here, you can just see it is just really, really, really dark. And that's what some of the surfaces of these objects look like. They're just incredibly dark. Maybe they're former comets that got a little too close to the sun and their ices got burned away. But basically, they are just really dark, and they're hard to spot with a visible light telescope. So if you have a heat-sensitive infrared telescope, it's preferentially able to pick out some of those very dark but still quite warm objects. So having complementarity in wavelengths as well as in just the area of the sky that a telescope can search is really helpful. And that's what we're hoping to do. So our new telescope is the Near-Earth Object Surveillance mission that we're hoping to build, NEOWISE. So anyway, we're about to undergo a series of reviews right now. So we're really looking forward to it.
Well, what about new ground-based searches. I've been hearing good things about this telescope that will be coming online, now known, just rechristened as the Vera Rubin telescope.
Yeah, this is a really exciting opportunity because basically this is a gargantuan telescope that's going to be in the southern hemisphere. So it will complement a lot of our assets that are currently in the northern hemisphere. This telescope is designed to take movies of the sky. So basically lots of exposures over every night, just really trying to cover the sky repeatedly over and over again, looking for transient phenomena. So exploding stars, things like that. And it will find lots of asteroids as well. The great thing about this is that if we have both of these capabilities, we'll be able to get the reflected light, the heat coming off the objects. When we put that together, in addition to be able to measure the sizes and find lots of them, we can now even say something about the surface reflectivity. And that gives us a clue as to what the asteroid is made out of.
Casey, I got one for you that I was not expecting, but it makes perfect sense. It comes to us from Eric Lipman. Is planetary defense a part of the mandate of the new Space Force?
It is not. So right now, Congress has designated NASA as the primary government agency responsible for finding and characterizing near-Earth objects. People bring this up a lot, and it's a reasonable question, right? You have national defense, so planetary defense may be part of that. It's generally argued that NASA as a civilian agency is better able to engage on a global partnership level with many other nations when you don't have kind of the politics of the military and national defense issues kind of wrapped up in that. So it makes it easier for data sharing, makes it easier for global partnerships. And at the moment, this is primarily a detection, discovery, and scientific endeavor more than it is a global military response. So the military itself tends not to want this responsibility either. You know, they have very sensitive, obviously, electronics and telescopes that they put into space. They tend to point downwards and not out. And so it's just not in their expertise to either to look out like this. Some assets are shared in the infrared spectrum and others, but it's, again, led by NASA, and I think correctly as the responsibility of NASA for this.
All right, here is one. Bruce, I'll throw this your way first, but then Amy, if you want to come in, it comes from Aurelia Waller. If an asteroid gets knocked out of orbit by the nature of multiple bodies in motion, how will those asteroids be tracked? And I assume what Aurelia is getting at here is, if one of these near-Earth objects flies by Earth, it's going to be deflected somewhat, right? How do we know that the next time around it's not going to hit us, Bruce?
It's a combination of observations and physical modeling. So understanding the physics of the perturbations as the asteroid goes past the Earth or gets affected from distance from Jupiter. But it's tricky. It eventually, when you go out tens, but particularly hundreds of years, thousands of years, the perturbations get very hard to model. But on the shorter term, we can do just as we do incredible work modeling the orbits of our spacecraft, getting them to places throughout the solar system. There are people whose expertise is taking these observations, if you've got enough of them, and plotting what's going to happen. But it definitely introduces the uncertainty in the process.
This is a tough one, isn't it, Amy? I mean, three-body problem, stuff like that. It's tough to calculate this stuff.
Yeah, absolutely. And one of the, I think the kind of unsung heroes of this particular field of study is computational. Basically, the computational infrastructure has improved enormously over the last 30 years. As you can imagine, it's just gotten incredibly easier to do these kinds of calculations. They were doable before, but much slower, much more difficult, much more painful. And now with the huge increase in the number of objects that we're tracking and that we know about, there's been a lot of work to improve the infrastructure to, first of all, connect all the orbits together, or connect the observations, I should say, to refine the orbital knowledge of a particular object, so before it makes a close pass. And then to also compute the impact parameters and really understand how far away it's going to be and will it get anywhere close to the Earth. So there's the Minor Planet Center, which is a key piece of infrastructure that basically has this humongous database. Every observation that people submit to the MPC, they keep track of. and they figure out which observation goes to which object, and has that object's orbit changed with time, especially if it's made a close approach. And then my colleagues at JPL do these very detailed, high precision calculations. And just like Bruce said, it's the same kind of calculation that you would use to predict the orbit of a spacecraft going far out into the solar system. Well, those same techniques apply to the minor planets as well. It's a lot of work, absolutely.
I'm glad you mentioned the JPL folks as well, where that Paul Chodas works. I mean, talk about heroes of the planet. I mean, I think people like Paul and others, some of whom I'm looking at right now, also deserve that title. Casey, here's one for you, I think. And it's one that I think I may have heard addressed elsewhere. Fascinating question from Michael Makowski. What can we learn from the global response to COVID-19 that can be applied to a global threat from a predicted NEO impact, or just preparing ourselves for something like that? Do any thoughts come to mind?
Yeah, I mean, it certainly makes me a little more worried about this. The global, well, let me rephrase that in a positive way. Something like COVID illustrates that these low probability events, when they manifest themselves, a lot of basic planning, there's only so much you can do, I suppose, in that, and a lot of it's going to depend on global integration and responsibility and communication. There's going to be a lot of issues I think we can learn about education and engaging the public in a rational and responsible way, but also preparing for disinformation and skepticism. I think we can also look to the idea of how different countries have responded differently based on a lot of particularly Asian countries that we saw. There's been some basic studies on this already that had a lot of engagement with pandemics or potential pandemics from SARS back in early 2000, tended to have stronger initial responses to controlling viral outbreaks earlier than countries that didn't. And so I think we can take lessons about that type of preparatory response and apply it to issues like planetary defense, where we can say, if we've had these types of engagements with leverage kind of public awareness of the importance of preparation for natural disasters, to say this isn't a very opportune moment to say, how can we use this lesson in terms of what we need to prepare for these types of things? So public, I think education, disinformation is a big part of that. And then also preparing a lot of the basic technology and understanding of deflection capabilities, right? What should we be doing now, and what types of infrastructure should we build into our systems that, as much as possible, can avoid the ups and downs of the political budgeting process, to say we have a sustained ongoing investment in the technology needed to rapidly respond to external threats. I think this is a very rich area for further analysis and comparison, particularly as we hopefully here relatively soon move beyond the issues of COVID as we move out of that. And I think we can more clearly look back and apply it going forward. I kind of made a connection in the paper we did to say we can even talk about these in COVID-like ways, to say that, you know, preparation can understand like the family of, you know, viruses is like understanding the characteristics and families of NEOs and potentially hazardous objects out there, right? We can develop effective treatments in advance by creating effective deflection techniques. And we can monitor for early breakouts in the way of monitoring for potentially hazardous asteroids with Earth. So I think even framing it in ways that are going to be very relevant to people is going to help us make that connection to say that, you know, one of the responsibilities we have as self-governing creatures as we is that we have to be able to put in basic sorts of preparation for these, again, these low impact or high impact, low probability events. And we can learn from the mixed response that we've had from COVID and definitely apply it to our lessons as we prepare for planetary defense activities.
I mean, here's an extension of what you're talking about, and it's built into what you're talking about. You have to wonder if we get the announcement that a big rock is headed our way, a world buster or a city buster, there's going to be a certain percentage of the population that is going to say, oh, look, the latest hoax from those scientists who are pushing for, global domination or something like that. It's very disappointing to consider, but it sure sounds like something that we'd have to talk about. Bruce, I mean, this is the kind of stuff that also comes up at PDC conferences and those desktop exercises.
It is, and there's discussion. Obviously, there's only so much you can do, but there's a lot of emphasis on how you communicate and getting the word out as clearly as possible. And you're always going to have that type of person, but by providing the information in clear and repeated ways through trusted sources with as much as you can, trusted spokespeople who know what they're talking about, you will alleviate that as much as possible.
I think one of the other important aspects of this is that the observations are set up in a way that is very transparent and replicable. So when the observations come in, when we are observing with our telescopes, we submit the observations, they go to the Minor Planet Center, and they publish them right away. Those observations are then transmitted to JPL. It's all an automated process, and the impact probabilities are computed and put up on public websites. So the process is designed for transparency so that observers all around the world can go and look for these objects with their own telescopes. And that helps us in so many ways because it allows us to refine knowledge of the orbits. It helps us to be sure that the objects really are there and doing what we think they're doing. And it helps us because one of the big hallmarks of science is replicability, the ability to repeat the experiment and get the same result. And we're really big on that in planetary defense.
And across all of science, hopefully. Bruce, I got one for you, I think. Outside, this is from Lee Stewart, by the way. Outside of having expensive equipment to actually track NEOs, are there any citizen science resources folks can use to help track or characterize these asteroids and comets? Does anything come to mind for somebody who, hasn't gotten a Shoemaker NEO grant and has a reasonably beefy telescope?
Well, one, you can get involved with Planetary Society. Had to throw that plug in, join Planetary Society. But there are people who sometimes put the data online. Some of our Shoemaker NEO winners, I know, do that with classrooms and educational groups, but a lot of it is done automated. I'll see if Amy knows of something more than I do.
Yeah, and for example, the recent comet was a really good example where we got lots of wonderful observations from people all over the place, and that has really contributed greatly to the understanding of the object, for example. So for one, just getting the observations of things that become bright enough to be detectable to small telescopes is really valuable. The other thing too is that there are archives of data that are out there that can be searched. I mean, for example, our data are actually, the NEOWISE data are public, and anybody can go in there and look at their favorite object and try to learn more about it. So there's some value in also just mining the existing data sets as well. But I think it's really a lot of this. I think the most important thing of all is just that that folks support science, support this kind of research, and just understand its importance. That really makes the biggest difference of all.
Yeah, Matt, I'd like to jump in and say there may not be, in addition to citizen science opportunities, there's certainly citizen advocacy opportunities here. As we've effectively been talking about, these things are very small and hard to find, right? So you have to be a very hardcore kind of unpaid professional or professional astronomers with good equipment to really engage with these things in terms of detection level. Or if you aren't that or don't have the time to do that, you can work through your political system to provide the resources to people to be paid to do this or to have the tools to do this. So either, to allow the NEO surveillance mission to move forward, to help us detect these things, to help more missions to practice and develop deflection techniques, to enable more ground-based observations to occur. And you do this through political action, through civic engagement with your political representatives, and we provide you at the Planetary Society with many avenues to do that. We have actions right now you can do to write your members of Congress, if you live in the United States, to support the NEO surveillance mission right now through the budget process that it's going through. So you can check that out at planetary.org/takeaction. or planetary.org/advocacy gives you a lot of background on these issues as well.
There
Casey,
are
I'm also,
oh, I was just
sorry, go
gonna-
ahead, Amy.
Sorry, I was just going to jump in. There are also some really cool citizen science light curve analysis projects that are out there, and I think we can get you a link to where you can find some of those, and maybe we can post that.
There's also just sharing what you learned. So part of the point of our toolkits that I mentioned, our infographics, the 1 hour roughly class that I did online, is to give you enough information that at least when you're talking to your friends, but maybe when you're talking to school groups, that you have resources and information to start sharing the basic facts about this and get the world better educated.
Yeah, the fact that the hundreds of you who are watching us right now are interested enough in this and are learning quite a bit about it, that puts you in a pretty special position. You can be a direct part of this effort, as Bruce has explained. And there's that other thing that where Casey, people can get directly involved by joining you in DC on that big day every year that was so successful just this last winter.
Yeah, right before the pandemic hit, we had over 100 society members come from 28 different states across the country to Washington, D.C. to meet with members of Congress and their staff directly. We're working on planning probably a virtual implementation of that for 21, but hopefully we'll all be back in person and advocating here in Washington, D.C. All together in 2022. So there'll be multiple opportunities for that coming forward.
I still hope they're inoculated in time for to gather in person in DC, so we can work on inoculating the planet from one of these attacks. Here's a question from Keith Burrell, and I'm going to paraphrase it a little bit. He's talking about one of the difficulties of looking for these objects from Earth, and it may be becoming even more difficult as we hear about these massive constellations of low Earth orbit satellites, like the one that SpaceX is building right now, but there's several more of these networks that are under construction. Amy, is this something that concerns you as an astronomer? I mean, it may not trouble your space telescopes, but it could be a problem from down here.
Yeah, this is something that the astronomical community is paying very careful attention to, as you can imagine. There have been a lot of studies that are going on right now, and I think the National Academy is working on this along with a few other groups. It's definitely a changing landscape and one that's moving very quickly. So, you know, one of the things we all want is cheaper access to space, but the flip side of that is that we can now put things in space more easily. And so that's kind of goes with the territory. So so there's a lot of attention now. Like I said, you know, there's several different aspects to this, of course. Just the sheer beauty of the dark night sky for all of us to enjoy. That's one thing. Obviously, space debris is another concern. We don't want things colliding and creating cascades of debris. That would be very bad. So there's a lot of issues here. And then, of course, there's how does it affect astronomical observations? For near-Earth asteroids, I will say it's generally not great. Because these things can be potentially confused. The degree to which it's going to affect the surveys is still to be determined, and it's still something that's being worked out right now. It depends a lot on the details of the constellation, how bright the satellites appear to be, how well we know their orbits and their positions, and so forth and so on, their altitudes, all that kind of thing. So there's still a lot that we don't know yet. But that said, I mean, this is the reality going forward that we are likely to have. Just like I said, that cheaper access to space has a lot of implications, and there are other concerns to be balanced on the other side. That said, that is partly why we like having space-based capabilities, because if it's outside of the orbital sphere of these mega constellations, we don't care, right? We just don't see it. The NEOWISE telescope is in about a 500-kilometer orbit. It's probably not going to last a whole lot longer. It is well past its expiration date as far as that goes. But the new telescope we're hoping to build is slated to be well outside of the orbit of the Earth-Moon system at the L1 Lagrange point, so it would be untroubled by these megasatellites. But you know, this is an emerging situation, and we have a lot to learn about it still.
Matt,
Casey, is the
can I add?
Planetary Society? Yeah, I was going to ask you if we've taken a position on this.
Well, we're certainly working closely with the community and particularly astronomical community, and they're really leading the way on this. So we're supportive of the work that they're doing at the American Astronomical Society and other places. I just wanted to add to this that people tend to flippantly say, well, if we have all these things in low Earth orbit, we'll be able to just make space telescopes, just move telescopes into space. And I think Dr. Meinzer can talk about the difficulty of getting these space telescopes funded. You have to build them, and they're not cheap. Putting things in space is more expensive than building things on the ground. And the struggles to get NEO surveillance mission built over the last almost, 15 years now, close. So tell us that we can't just move all of our observational capability into space without any problem. It's going to be a huge impact either way. And so even modest space telescopes can be hard to get funding for. And that's something we need to be very aware of as we impact the ability to pursue science in the night sky.
Some of you watching us who've joined us today probably have noticed that we're already past our nominal end time for this discussion. But if the three of you are able to stick around for a couple more minutes, there are a couple more things that I would love for us to talk about. And Amy, I gave you presenter rights again. We're not going to do this just yet, but there is that beautiful comet of yours that I'd love to see some of those images. Maybe we'll close out with that. The topic that I'd love to get to, though, before we do that, and by the way, thank you to all of you who continue to submit questions. As always, and I've said this, I don't know how many times already, we simply never are able to get to all of these, but we do have a record of all of them, and you will not be forgotten. Something that we have not yet talked about is the simple value of the science that we can do as we study these bodies in space. Separate from the threat that they pose to our planet, there is so much great science, so much to learn from these objects. Amy, I want to hear from you, and Bruce, you as well, about this.
Yeah, one of the really wonderful side benefits of doing these big surveys is we find all kinds of interesting things. And it gives us the opportunity to go and study some of them really up close, and maybe even bring pieces back that we can study in our laboratories when they haven't been fried by the Earth's atmosphere. So for example, NASA's got a mission called Osiris-Rex that's actually orbiting a near-Earth asteroid right now, and it's just about to go take a sample. I think that's in October, so next month it's coming right up. They're actually going to touch down and get a piece of the rock and bring it home. So I personally can't wait to see what they find. That's going to be really cool. I don't know, Bruce, what's your favorite?
Oh, it's kind of like with kids. I don't like to pick my favorite, but I will mention also that Hayabusa 2 is sampled an asteroid Ryugu, the Japanese space agency, and it's actually returning samples this December, dropping them into Australia. So it'll be fun to see what they get. We've got Osiris-Rex doing their sampling. So yeah, I mean, there's a lot of great science there. It's amazing the variation that we see in these asteroids. And all you have to do is look at some of the spacecraft images of asteroids to see their shape variations, but they also go from rubble piles to fluff balls to other silly names to hunks of metal. And so it's there's a lot there. Also, a lot of these asteroids are leftovers, remnants from the early formation of the solar system. So by studying these objects, we're getting information about planetary formation and evolution of the solar system.
Something I'd
Great
like to
stuff.
add just to that, just to keep in mind, just to remind everybody how new all this is that the first dedicated mission to an asteroid wasn't until I think the NEAR mission in '94. So that was just 25 years ago. And we had some flybys with Galileo, but now there's been a huge explosion. You can see this, and I compiled this planetary exploration budget data set to see how money is being spent on various planetary missions. The small bodies section of that budgeting and spending that NASA's been doing over the years has only been the last 25 years into near-Earth objects and asteroids themselves. So this is a very new field, and the fact that we have missions dedicated to these objects now is relatively recent phenomenon. So this is something that we can all kind of appreciate, that we're still exploring these brand new areas And I'll just put in a pitch that I'm excited about Psyche coming up.
I was going to bring up Psyche and Lucy missions that are in preparation right now. Amy, can you say something about those? And of course, we also have DART that we've already talked about.
Yeah, this is kind of a golden age in a lot of ways for exploring the small body populations. So the asteroids and comets in our own solar system. And it's really a wonderful chance now to get to visit some of them. I'll even mention the New Horizons mission. So we've got Psyche, which is going to an object that's possibly a metallic shattered core. We've got Lucy going to the distant asteroids that are sort of captured into a resonance by the planet Jupiter. And then the New Horizons spacecraft, of course, did its amazing flyby of Pluto and also a Kuiper Belt object, a very distant and extremely cold, icy thing that looks like kind of two lumps stuck together. So that was pretty exciting. So we have a lot of really good stuff coming up, and we have a lot more to learn, so much more to learn. But they're really fun objects to explore. They're constantly moving, and sometimes, you know, they can really surprise us.
Just got a thumbs up from Alan Stern
too.
for thumbs up from Alan Stern for including his mission, New Horizons, and all of that. Amy, there is also an element of passion, beauty, and joy in all of this, the PB&J that Bill Nye loves to talk about. Take us out, if we're able to share your slides. You have some gorgeous images of that comet NEOWISE. Let's see if we can bring this up again. I've made you the center.
You got it. Let's see if this is shot here. Okay, let me put this into presenter mode and we'll see if it works. Fingers crossed. Do we have success? Oh, let's try it again.
Oh, I'm just, yeah, I'm only seeing a white screen. There you got it.
It works. Okay, fabulous. We can send spacecraft across the universe. Can we also get PowerPoint to work?
The final frontier here, presentation software.
That's exactly right. So this is an image of an object that we found in late March, and with the NEOWISE mission, and our team discovered this in the data. And here's 3 of the discovery images. I've digitally combined them so that you can see the object moving across the sky. And this is what I was talking about. They just look like little chains of dots, but in this case, these were fuzzy dots. So we were able to tell right away that this was a comet. It wasn't matched up with anything else. And as soon as we were able to get some follow-up observations from our observer friends on the ground, we were able to tell that it was going to make a very close pass by the sun in July. So this just gives you an idea for how quickly these things can kind of sneak up on us, and how fast they can come up. Comets move really quickly. And in this case, this is a pretty big object. It's about 5 kilometers across from our infrared data. And we can also get some other information about its particle sizes that are getting fluffed off into the coma, as well as the gas emission. So that's what it looked like when we first spotted it. And when it got close to Earth, these are just some of the amazing images that people all around the world collected, which was really a lot of fun to see. This is my colleague Vishnu Reddy at the University of Arizona who took this photo, appearing with the aurora.
Gorgeous.
With the cactus. Even from space. The astronauts on the space station were even able to capture an image of the comet there off to the left. This is really kind of fun. It's really kind of a neat backdrop. Now that's an engagement photo, folks. And finally, here it is over Hollywood, over a castle, and one of my favorite shots right here. So these objects have touched human life in many different ways. It's not just it's not the impacts. It's actually just the profound effect that it has in reminding us that we are connected to the universe. And I'll just say that we actually just discovered another one that's going to be making a close approach, similarly close to this previous comet in October. So keep your eyes peeled for that one. There's another Comet NEOWISE coming pretty soon. But I will just say that one of my favorite things about all this is I went out to see the comet one night, and I thought I'd be on a nice dark stretch of road and able to get a good clear view of it. And there were all these cars and people had their headlights on, and I was really annoyed at first. And then it took me a minute to think about it. But then I realized, you know what? They're here to see the comet. And that's really cool, especially now with the pandemic and all that's going on. So that was really special.
Space brings out the best in us. Another quote from our boss. Bruce, we got to try and catch one of these in the sites of LightSail 2.
Yes, we are optimized with Light Sail 2 for observations. No, we're not. We're not. We're a
Just
solar
a sneaky way of including our sail.
We take pretty pictures of Earth. We have captured the moon, and it's stunning at 5 pixels across. Yeah. I'll give some, well, I'll let you make a smart aleck comment, and then I'll give some final words.
No, please go right ahead.
Okay. Just a reminder that this is a large-scale natural disaster that we can actually do something about. And people like the people here and the many professionals and amateurs working on this can make this a preventable natural disaster, and that it's a low frequency event. But on the other hand, if you wait long enough and you don't do anything, the probability of impact is 100%. So let's go out there and do some good. Thank you. Good night.
And good night. Casey, any closing thoughts?
I don't have much more to add than what's already been said, but just to emphasize, in addition to the scientific work, all the it's enabled fundamentally, I'd say, by the political support. And so this is why we try to take this two-tiered approach to it, with the work that Bruce does at the Planetary Society, and then the work that we do at the advocacy and space policy to help support scientists like Amy really pursue these advanced and ambitious missions to ultimately save the planet. So it's one of the most, I'd say, impactful, but maybe that's the wrong word to choose, political things that we can do, is to, again, modest increases in these budgets can have significant consequences, positive consequences for our preparation and ability to track and characterize these things. So it's a really achievable goal.
Amy, keep up the great work. I look forward to hearing more about NEOSM and welcoming you back to Planetary Radio. And Bruce and Casey, of course, I'll be talking to you there as well. Thank you.
Thank you, Matt.
Thanks, Matt.
Thanks
We're
for
at the end
letting
of
me be here.
You bet, of course. We are at the end of today's Planetary Defense Update. Again, I'm sorry we didn't have time for more of your questions. You can continue to submit them offline. We will get a record of all of those. One more time, I want to thank our superb panel, Amy Mainzer, Bruce Fetz, and Casey Dreier. And again, thank you, not just for joining us today, but for making all of our work happen, whether it's as a member, a donor, or both. We literally could not do any of this without you. To learn more about our planetary defense activities and to become part of it through your gift, visit us at planetary.org/defense. The planet you save may be your own. I'm Mat Kaplan of the Planetary Society. I will see you on the radio at Astra, everybody, and at Asteroid too.